Okay, today we're going to learn about optimization. And optimization is used to solve real life problems, and we use it to find minimums and maximums of a function. So there are 7 steps to follow when doing optimization. The first step is make sure you read the problem carefully and understand the problem, identify the information you need to solve the problem, and what you have been given. The second part is develop a mathematical model of the problem. Draw pictures and label parts that are important to the problem, and let a variable represent the quantity to be maximized or minimized. Using that variable, then write an equation for the variable you are trying to maximize or minimize. This is the mathematical model. You're going to need a second equation generally with the constraints given in the problem, and you always want to get the problem in terms of one variable. The fourth step is to determine the domain of the function and determine what values of the variable make sense in the problem. Then you're going to find the critical points and the endpoints, find where the derivative is 0 and fails to exist in order to find those critical points. And you're going to use the second derivative test to determine if the critical points and endpoints are maximums or minimums. And the last part is you interpret the solution. You answer the question by writing what they asked for in the problem. So the first example is we have been asked to design a 1-liter oil can shaped like a right circular cylinder, and it says what dimensions will use the least material. Alright, so for step 1, we're thinking about what are we trying to do. So we're trying to minimize the surface area, and we're given the volume of the can. For step 2, we want to write the formulas, and they told us the formulas, but the formula for surface area, which we're trying to minimize, is 2 pi r squared plus 2 pi rh. And the reason we're doing surface area is it talks about what is the least material we can use. So if you think about the material, that's going to be covering the surrounding can, so that's surface area and not volume. Step 3, we also have to identify other things that we've been given. So we have been given the volume of the can, and so the volume of the can is 1,000 centimeters cubed. So I'm going to set pi r squared h equal to 1,000. And the goal is we need to get it in terms of one variable so that we can take the derivative and solve. So I'm going to solve for h, which we did over here, by dividing by pi r squared. So I have 1,000 divided by pi r squared, and then we can plug that in for h in our formula. So if you look here, we substituted 1,000 pi r squared into h, and then we simplified the equation. So my equation that I'm going to minimize is 2 pi r squared plus 1,000 divided by pi. And now we're just going to use the steps we learned last chapter to find the minimum values of a function. So first thing though, we have to make sure we know our endpoints because we always have to check them. So if we think in real life, when we talk about a can, the radius and the height both can't be less than 0. So our domain is the radius is greater than 0. You can write the height is greater than 0, but since it's in our not in our formula right now, it doesn't really matter. And then we're going to find the derivative. So here we have the derivative of the area with respect to time, or it should be with respect to r. So this should be an r and not a t. So with respect to time, if we take the derivative, remember pi is a constant. So we have the derivative of 2 pi r squared is 4 pi r. And the derivative of 1,000 divided by r, remember, is this is the same as 1,000 times r to the negative first. So if we take the derivative of that, we do 1,000 times negative 1, and then we subtract 1 from the negative, so we get r to the negative second, which is the same thing as 4 pi r minus 1,000 divided by r squared. To find the critical points, we set it equal to 0, which we finished in step 5, and we solve it for r, for our radius. So if we set it equal to 0 and we solve, what we would get is we need to, how we solve this, if we have 4 pi r minus 1,000 over r squared is equal to 0. If I get a common denominator here, this needs an r squared, so I'm going to multiply top and bottom by r squared. And so I get 4 pi r cubed minus 1,000 over r squared equals 0. So one critical point is r equals 0 because that where the denominator is undefined. And then we set the numerator equal to 0 to find the other critical points. And so I get 4 pi r cubed is equal to 1,000. And then I'm going to have r cubed is equal to 1,000 divided by 4 pi. And then 1,000 divided by 4, if we do that, is how we got, should be actually 250. So we have r cubed is equal to 250 over pi. And so r is equal to the cube root of 250 over pi. Okay. So here this should actually be 250 and not 500. Okay. Then the sixth step is we need to figure out if it's a max or min. So we're going to plug this number, and in order to make sure it's exact, you either need to plug this in or store it into your calculator, but we're going to plug it into the second derivative. So we have to take the derivative of this, and if we take the derivative of that, we get 4 pi plus 4,000 r to the negative third. This is the simplified version here, and then I'm going to plug in, we'll plug in actually 250 over pi. And again, all we care of if it's positive or negative. So I'm going to have a positive plus a positive. It's a positive. So this critical point is the minimum. And then we have to make sure we check endpoint. So the only endpoint is r equals 0. Okay. Which would give you a 0 surface area, which is not possible. So we don't really need to worry about that. But always make sure you check those endpoints because sometimes they will be your answer. And then we find the value. So if we solve for r, if we get that as a number, I'm going to take the cube root of 250 divided by pi. And we get r, the radius, is actually 4.301. And then I'm going to have to fix my height. I'm going to plug in 4.301 into my height equation, which is all the way up here. So I'm going to say h is equal to 1,000 divided by pi, and then the 4.301 squared. And remember, you need to store the 4.301 in your calculator to get the exact value because it has to be accurate to 4 decimal places for you to get credit on the AP exam. So if I get that, I get the height to be 17.205 centimeters. And so these are the dimensions that give me the least material, that minimizes the surface area. Okay, so for a second example, we have a box with a square base. It has an open top, and the volume is 4 cubic feet. And we want to find the dimensions that require the least amount of material. Okay, and they said don't care about the thickness. So again, we know volume is equal to 4 cubic feet. Okay, and we want to minimize, and again, we want the least amount of material. So we want to minimize surface area. So if we have a cube, if we say x is equal to the base, or the length of the base, and y is equal to the height of the box. Okay, so here's my box. Sorry about the drawing. And then if we say the base, the length of the base is x, it's a square base. So both of the sides are x and x, and then the height, this length, would be y. The height is the distance between the two sides of the boxes. Okay? And there's this side we're going to say is open. Okay? So if I want surface area, what I'm doing is I'm finding the area of each side and adding it together. So we need to figure out the formula for surface area. So if I take this front box, it would be x times x, so it would be x squared plus, and then the side would be x times y, and there would be 4 sides on the box. So I would do plus 4xy, and that would be my equation for surface area. This is the equation I'm going to minimize. Now, we need to get this all in terms of one variable, so we need a second equation, and they told me the volume. So I'm going to use that equation. Now the volume of a box would be the area of the base times the height. So it would be x squared times y. Because usually the volume of a prism is length times width times height. And we have to write our domain. So realistically, the length of the base has to be greater than 0, and the length of the height has to be greater than 0. So those are my two restraints that we know. Okay? So if we do this, we need to get it in terms of one variable. So I'm going to plug 4 in for the volume, and I'm going to solve for one of my variables. It is easier to solve for y, so I'm going to solve for y. Always pick the variable that it's easiest to solve for. And then I'm going to plug it back into the surface area formula because I need it in terms of one variable. And then we can simplify this equation. So this is my surface area equation that I'm going to minimize. So now we're going to use the process that we learned to find our critical points and to find if they're min and max. So I'm going to find, and I'm going to change surface area to A just to make it easier. I'm going to find A prime, or dA over dx, which is 2x. And then remember, 16 over x is the same as 16 times x to the negative first. You can also use product rule if you prefer, or quotient rule, quotient rule if you prefer. But it would be negative 16 x to the negative second when I take the derivative. So we're going to set this equal to 0, and I have 16 over x squared. And then we can get a common denominator, so this needs to be multiplied by x squared, so I have 2x cubed minus 16 over x squared. And so my critical points are going to be x equals 0, and then I'm going to set 2x cubed minus 16 equal to 0. And so we have 2x cubed is equal to 16, x cubed is equal to 8, and then x is equal to 2. Okay, so my critical points are 2 and 0. Now, 0 is not in the domain. And unrealistically, it's unrealistic to have x equal to 0 or y equal to 0. So we don't really have any endpoints to check. So our only critical point is x equals 2. And we have to find if it's a min or max, and we're going to use the second derivative test. So I'm going to check if it's min or max by plugging this in, 2, into the second derivative. So I need the second derivative. So this is to check if min or max. Okay, so the second derivative is 2, and then again this is negative 16 times x to the negative second, so I'm going to have plus 32 x to the negative 3, and I'm going to find a double prime of 2, so I'm going to have 2 plus 32 divided by 2 cubed, and this is going to be a positive, so that means at x equals 2, A is concave up, and x equals 2 is a minimum. You always have to check that. And then we need to find, they said, the dimensions. So we found the length of the base. We need to find the length of the height, which is y. So I'm going to plug in 2 into my equation for y, which is right here. So I'm going to say y is equal to 4 over 2 squared. So it's 4 divided by 4, so it's 1. So my dimensions are 2 feet by 1 foot. Okay. So, which would minimize the surface area. Okay. And if they ask you to justify or in a complete sentence, you would say that the length of the base is 2 feet and the height of the box would be 1 foot. And that would give you the minimum surface area for a box with a volume of 4 cubic feet. Okay, so a second example is we have a builder wants a rectangular pen with 3 parallel partitions using 500 feet of fencing, and what dimensions will maximize the total area. So we want to maximize, and we're maximizing area. So if they don't give you a picture, always draw a picture. So we want a rectangular pen. So I'm going to draw a rectangle, and it has 3 partitions. So it's divided into 3, or it has 3 parts. And they want to use 500 feet of fencing. Okay, so if we want to maximize area. Now, if we think about this, we can call variables. So if we call this my lengths of this side, x's, so those are my partitions. And then we can just call all this length y. Okay, we assume that they're equal distances, but they didn't necessarily tell us. So we'll just call this whole length y. Right. Now, this 500 feet of fencing, and always look at units, is talking about how much fencing. And so that's the length around the outside, so that's perimeter. So we know the perimeter is 500 feet. Okay. And if we look at this, for the perimeter, we have 5 x's, so it's going to be 5x plus 2y. If you really wanted to break each of these up into y, you can, it doesn't matter. You would just have then 4y or 8y total instead of this. But if you just leave it as 1y, it's going to be easier to find the area. So for area of the pen, we want the area of the whole pen. So it doesn't matter how many parts it's divided into, the area is going to stay the same. So I just need the area of the outside, which is x times y. So I'm finding the area of the whole pen, which is x times y. And again, x has to be greater than 0 and y has to be greater than 0, or else we wouldn't have any area. So we use our perimeter formula in order to get this in terms of one variable. So I'm going to set 500 equal to 5x plus 2y, and I'm going to solve for one of the variables. I just decided to solve for y. It doesn't really matter. So I'm going to do 500 minus 5x, and then I'm going to divide it by 2. So I have 250 minus 2.5, and that's my equation for y, and I'm going to plug it into my area. Right. And I'm going to find the derivative. The easiest thing to do with these is just to multiply it out first, so you don't have to use product or quotient rules. So if you can simplify on these problems, always do. So I distributed the x, and now I'm going to find the derivative. So I get 250 minus 5x is my derivative. And then I'm going to set it equal to 0 to find my critical point. So I have 250 is equal to 5x, and x is equal to 50. Now we need to check if it's a max, so I'm going to take the second derivative, and if I take the second derivative of a prime, I get negative 5. Now that means the second derivative is always negative, so it's always concave down. So x equals 50 is a max, and we're trying to maximize it, so that's good. And then we need to find the dimensions, so I need to plug in 50 into y. So I'm going to plug in 50 for x to get y. And if I multiply that out, I get y is 125. Now we always include units. So the dimensions of the pen are 50 feet by 125 feet. And that would maximize the total area of the pen. So the hardest part is just coming up with the equations. Once you get that, it's everything we've done before in Unit 5 or Unit 4. Okay. So this example 3 is very similar to the second example that we did. So if you want to pause it and try it yourself and then check your answer, you can. But we have an open rectangular box and it has a square base. So we have a square base and it's an open rectangular box, so there's no, sorry, I cannot draw, but there's no top. So this part is open. Okay. And again, it's going to be made with 48 square feet of material. Now this is key. Square feet implies area. So we're talking about the surface area is 48. Okay. And we want the dimensions that give us the largest possible volume. So we want to maximize volume. Okay, so we need our equations for volume and surface area. Sometimes they will give them to you, but it's not a guarantee. So if we think about this, volume, again, is the area of the base times the height. So let's let x equal the length of the base and y equal the height of the box. So the volume would be the area of the base, which is x times x, or x squared, times the height. So that gives me the volume. This is y, x, x. That's the volume. Surface area formula, we have to find the area of all the sides and add them together. So we have one base because it's open top, so it's x squared. Plus, if I find the area of one of the sides, it's x times y, and I have 4 sides, so it's plus 4xy. And we know that this is equal to 48. Okay, so for this problem, we need to again get volume in terms of one variable in order to find the critical points. So for this, in order to do this, we need to solve for one of the variables. The easiest one is y, since there's only one. So I'm going to subtract x squared, and then I'm going to divide everything by 4x. Right. Generally, for these problems, I simplify as much as possible because then I don't have to use my product and quotient rule. If you prefer to use the product or quotient rule, that's fine. But I'm going to do 48 divided by 4x, which is 12 divided by x, or 12 times x to the negative first, and then I have minus x over 4. That's equal to the area, or to y. And then we need to plug this in to my volume formula. So I'm going to have V is equal to x squared times 12 over x minus x over 4. Again, I'm going to distribute, so I don't have to use product rule. So I have 12x minus x cubed over 4. And once you get that, it will be, this problem should be easy. We just take the derivative to find the critical point. So I have 12 minus 3x squared over 4. I'm going to set that equal to 0 to find my critical points. So I have 3x squared over 4 is equal to 12. I'm going to multiply by 4. So I have 3x squared is equal to 48. I'm going to divide by 3. So I get x squared is equal to 16. And then I'm going to get x is equal to plus or minus 4. Okay, so for this, we get these two values. We have to check if they're in our domain, and I forgot to write the domain. So if we come back to this, remember, in order for it to make sense, x has to be greater than 0 and y has to be greater than 0, because I can't have a negative height or base, and I can't have a base or height that's 0 because it makes a non-existent box. Okay, so if I look at my critical points, the only one that matters is x equals 4, because x equals negative 4 is not in the domain. So we have to check if it's a max or a min to make sure we're maximizing volume. So I take the second derivative of volume, which is 12 minus 3x squared over 4. I plug in 4. So I get 12 minus 3 times 16 over 4. And then if I do that, I get 3 times 16, which is 48, divided by 4 is 12. Okay, so hold on. This is still the first derivative. I took the derivative of v again. So if we erase this to go back again, sorry about that, we need to find the second derivative. So I need to take the derivative of v prime. So if I do that, it's negative 6x over 4. And if I plug in 4, I'm going to get negative 6 times 4 over 4. It's going to be a negative. So it's concave down, and x equals 4 is a max. So we are maximizing it. And then we just need to find the other dimension. So I'm going to plug 4 into my y equation to find the length of the y. So I have y is equal to 12 divided by 4 minus 4 divided by 4. So I have 12 divided by 4, which is 3, minus 1, which is 2. So my dimensions are 4 feet by 2 feet. Okay, and x is the length of the base, and 2 is the length of the height. Alright, so the last problem we're going to do in this lesson, and then the other ones we're going to try in class, and you should read through the examples because they have extra examples in the textbook, is we have at noon a cruise ship is 30 miles south of a sailboat B and is sailing north at a rate of 24 miles per hour. And if the sailboat is sailing west at 10 miles per hour, find the time at which the distance between the ships is a minimum. So we're trying to minimize time, and that's key because we need to get the equation in terms of time. So always draw an equation, picture. So we have a sailboat B, and we have another sailboat that is 30 miles south of it. Okay? And this B sailboat is traveling north, so it's going this way, or sorry, traveling west at 10 miles per hour. Okay? And the sailboat A is actually traveling this way at 30 or at 24 miles per hour. So they're actually decreasing this distance. And we're trying to find the time when the distance is a minimum. So we're trying to, if it's moving this way and that's moving up, the distance between the two ships is going to be this distance. Okay, so that's our D that we're trying to minimize. And we want to find the time. So if we look at this, we created a right triangle. And so we'll use Pythagorean theorem in order to relate it. Okay, so we're going to call this distance y, and then the distance that he's traveling is x. And we have to be careful about that. So we're going to say y is the sailboat, which is B, is the sailboat's distance traveled. And x is the cruise ship, which is ship A. distance traveled. Now, what we have to be careful is that this distance is not just x, okay? X is how far the cruise ship traveled. So it started 30 miles away, and then it traveled x, the distance of x. So this length is actually 30 minus x, because we're taking the total distance, subtracting the distance that it traveled. And then we're going to use our Pythagorean theorem. So we have d squared is equal to y squared plus 30 minus x squared. And that is my equation. Now, our goal is we're trying to minimize time. And so I need to get this in terms of time. So if you go back to probably Algebra 1 and we think about what distance equals, distance is equal to rate times time. Or if you're taking physics, you might be doing that as well. So y's distance is equal to the rate that the sailboat is traveling, which is 10 miles per hour, times the time. And now we have it in terms of t. And x is the sailboat's speed, which is 24 miles per hour, times time. And so we can plug these into our equation. So if I take this and I plug it in for y, I get 10t squared plus 30 minus 24t squared. Now I have it in terms of time, and so I can minimize time. And we want, in order so that we don't have to know anything about distance, we're just going to solve for d. So I'm going to take the square root. Because otherwise, if we don't, then we have to find the distance. So it's easier just to always solve for the variable we're trying to maximize or minimize. Okay, this is the hardest part of the problem. Once we get the equation, it's a lot easier. And this is usually the hardest type of optimization problem. So I need to take the derivative to find out the critical points. So I need to use chain rule with 1/2. So my outside's 1/2. Keep the inside the same. Raised to the negative 1/2 times the derivative of the inside. So the derivative of 100t is 100. And then I need to use either square this or use chain rule again. So I'm going to use chain rule again. So I'm going to bring down the 2, keep the inside the same, and I'm going to multiply by negative 24, which is the derivative of the inside. Okay, so this is my long derivative, and I need to simplify it. So I have the derivative is equal to, I'm going to move my square root to the bottom. So I have it over 2 the square root of 100t minus 30 minus 24t squared. And then my top, if I simplify this, I have negative 2 times negative 24. So that gives me a positive 48. So I have 100 plus 48 times 30 minus 24t. And then I need to, if I multiply this out and simplify, I get 48 times 30, which gives you 1440, and I get 48 times negative 24. Okay, so I have 100 plus, and then 48 times 30 is 1440 minus 1152t all over this 2 square root and then everything under the square root. Okay, if we just go back a second, I realized I made a mistake. So this is 100t squared, which makes this 200t. So this is going to be 200t, and this is going to be 200t. So just please fix that because I messed up that derivative. And then on this, we can combine our like terms. So I'm going to do 200 minus 1552. So I get the derivative is 848 t plus, nope, hold on, subtracted that wrong. So the derivative is negative 952t plus 1440 is equal to 0. And then we solve it. So I get t is equal to 1440 divided by 952. So t, our minimum time is 1.5126.